Hello everyone and welcome to the 48th lecture of the course Advanced Structural Analysis. We have discussed the basic formulation of the beam problem using the geometrical nonlinearity in the given system. Now with this week we will be discussing some of the example problems, and in the analysis somewhere, as we discussed earlier, the simple problem of the truss in the given system, we formulated the beam problem on the similar format. The last session looked at the basic problem of the general equilibrium of the system as well as the standard kinematic expression of the system, but we have not identified the full kinematic expression in the system, which we would like to identify from this given session. So, this is the basic discussion which we will try to cover. We will identify the basic kinematics of the beam problems, which is possible for the large deformation problems. Then we will also try to identify the incremental stiffness approach similar to the what we did in the trusses, and we will try to identify the nonlinear and the geometrical stiffness contributions of the given problem. So, if you recall the discussion from the last lecture, we identified the strain in the given member of a beam. We considered that strain in general can be identified with this expression, where the epsilon x is the only amount of the longitudinal strain in the given system. While defining this system, we are considering that the beam member is subjected to pure flexural conditions, but at the same time the axial loads are also active on the given system. So, which means that the axial change in length of the member is also permitted, and that is one necessary feature of the large deformation problems, because somewhere we understand that the responsible feature which typically modifies the stiffness of the problems in the large deformation cases is the axial load active on the given system. And to consider that into the formulation, we have also adopted the axial deformation for the given system. So, with this part we adopt that the strain is identified as the very regular expression del u upon del x plus half del v upon del x whole square. The second term which we have identified here, this is the contribution which typically is added due to the large displacements in the given system. Had it been only the small displacements, so we could have just gone with the first term in the given system. Then we considered the expansion of the displacement field, which was with respect to the u parameter, and which we have, I think if you recall from the last discussion, we defined as that u for the given system in effective manner can be defined as u bar, which is the pure extension, into y times theta for the given problem, and of course, this is also in the member coordinates of the given system. And then we can also define this as y times del of v bar upon del x, which typically means that the rotation of the given transverse normal is same as the rotation of the axial line of the given member, which is the slope of the given problem. So, this comes out from the very standard point that we are not considering any shear deformation in the system. So, the transverse normal remains normal to the reference surface. So, in case if the normal was defined in the undeformed configuration, it was making an angle of 90 degree. As the system has undergone some deformation, and due to that the axial line has modified, the transverse normal also gets modified, but it maintains the 90 degree angle with the given system. So, this rotation which the system has adopted is typically defined by the same slope, which is the slope of the given member in terms of dv upon dx of the given problem. With this idea in mind, we were able to identify the overall strain in terms of two parameters. One was the strain with respect to the generalized term of the del u upon del x and half of del v bar upon del x square. The second term was corresponding to the curvature parameter, and this is now we can identify that both of these terms are now only the function of x, which is the local coordinate of the member length, whereas the other coordinates which were identified with respect to the thickness direction of the system has been separated from the given field. So, we are not going to include this in the final formulation. So, that is why we have considered them separately from the given equation. In a simplified manner, we can also write this equation as 1 y into epsilon, where this epsilon expression is typically utilized as a vector representing epsilon x naught and the curvature term kappa x in the given system. Now, with these 2 points, which are the pure stretching and the curvature terms of the given system, we identified their individual expressions which were located based upon the general kinematic condition. But what is defined over here is a continuous expression of the displacement, which means that if I have this as a member which is having 2 of the nodes, I can know the displacement variation with respect to the given point from one end to the second end based upon a continuous function using these expressions, but I do not know the variation of the displacement at any intermediate point of the given system if I know the displacements at the ends of the given problem only. So, what we mean to say is that typically when we are trying to solve the problems using the general structural analysis approaches, we identify the displacements at the nodal points. Now, the displacement values which are identified at the nodal points are typically expressed such that at any other intermediate point of the given system also, if we want to define the value of the displacements parameter or the strain parameters of the given system, we can express them in terms of the same nodal values of the given system. So, if you recall the way we identified the standard stiffness in the given problems earlier, we always try to identify the standard stiffnesses with respect to the form that P equal to K delta, where delta happens to be the standard value at the nodal points of the given system. So, now knowing the values as a general function is not something which is meaningful for our further analysis. So, what we require now, what is the variation of the u bar and v bar across the length, that we need to know first, and then we also need to identify, can we express the general variation in terms of the primary displacement parameters of the given system, which happens to be u 1 bar, v 1 bar, theta 1 bar at one of the node, u 2 bar, v 2 bar and theta 2 bar at the second end of the given system. We always make this point clear that theta bar at any of the point, say any point I of the given system, is typically denoted as dV upon dx at the given point I of the system. So, with this idea, now we realize that we need to express our strain expressions which are defined as a function of x in terms of a parameter where the displacements are not defined by the continuous function field, but rather with respect to the standard nodal values of the given system. Now, this is a standard problem which typically we solve when it comes to the standard finite element approaches also. We will take a small hint from the finite element based formulations of the system to identify these relations, but the content which we will be discussing over here has not much intention to cover the finite element in a more generalized form. So, what we understand as we take up the variation with respect to the given system, we consider that corresponding to this point, say if it is point x equal to 0, of course, this is the local coordinate, but right now I am just writing it as x in general, so that we can define the coordinates at the beginning. For maybe for the generality generalization, one can also put x bar in the given formulation. So, this is the point which is x bar equal to 0, and if the length of the member is total L, I can define this value as x bar equal to L in the given problem, and say at any intermediate point I have a value of x bar where I want to define the value of the displacement in the given system. So, if I want to go with the value of u, which is the in plane displacement, again I define it in the local coordinates, I can say that as it is only dependent upon, I am looking for the answer to be dependent only in terms of these two parameters of the system, which are u 1 bar and u 2 bar. So, I can approximate it with respect to a simple linear function. So, what is the intention of it, that if I have 2 points which I know the probable values or for which I want to express the given function, so I can only generalize a standard linear function for these 2 points based upon the available set of equations. So, using this idea, I can write the standard form of the equation as a into b of x bar in the given system, which means that if I consider that u bar at the value of x bar equal to 0, it will give me a, which is the value of, so I would just say that it is the value of a, which is the u at the value of x bar equal to 0, and that value is u 1 in the given system. So, a happens to be u 1 bar in the given system. Similarly, if I go with the function again and I call it as that u bar at x equal to L in the given problem, and I realize that if I substitute this value x equal to L in the function, it gives me a plus b into L, and I realize now that this value u bar at x equal to L happens to be the value of displacement over here, which is u2 bar. So, I can call it as that u2 bar is equal to A plus B of L. So, I got two set of equations which I can solve easily, and I can get the values of two unknown parameters A and B in the given problem. If I do this, what it gives me in general system, so I write it as u, A is already calculated as u1 bar, so I write it as u1 bar plus B we evaluate from here again, and B comes out as u2 bar minus u1 bar upon L in the given problem. So, I just took A on the other side divided by the L value, and it comes out as the standard expression. Now, with respect to this parameter, I realize that u2 bar minus u1 bar upon L into x bar happens to be the displacement variation with respect to the longitudinal direction x bar in the given system. Now, what does it necessarily also mean? If I break it down further, I can write it as u bar is equal to 1 minus x bar upon L into u1 bar plus x bar upon L into u2 bar. So, I did not do anything more, I just considered the coefficients of u1 in one basket, and I considered the coefficients of u2 bar in the second basket. The moment I do it, I can write this expression now as a very generalized form in which u bar has been expressed as the parameter dependent upon n1 and n2. Let me call that n1 is this function and n2 is this function 2 of the given system, whereas I can consider them multiplied by the u1 bar and u2 bar in the given system. So, if I just multiply this vector with the second vector u1 bar and u2 bar, I will end up with the same expression which I have just generalized. But what is the utility of having this expression? We realize initially that u bar was appearing as a function which is defined in terms of the x and which is not known to the user. So, if I write that u bar was initially a function of x, now I have converted it into the two part of the expression where n1 and n2 happens to be the functions which are dependent upon x of the system. So, n1 is also a function of x, or rather I should say x bar, because the local coordinate we are defining. Similarly, n2 also happens to be a function of x bar in the given system, whereas the u1 and u2 bar, which are the which are the identified fixed set of values at the two nodal points, now they are appearing in the system which are completely independent of the x in the given system. So, whatever variation of the x I required in the system has been already adopted in the variation of the n1 and n2, which happens to be the standard shape functions of the given system, and u1 bar and u2 bar, which are the nodal values of the given system, they have been just separated from the given system, which means that now the user is able to know that what is the variation of the displacement function u bar across the length of the given system. Not only that, the user is also now able to break down the variation of the u bar in terms of the nodal values of the given system. So, if I now want to define the u bar as a function only in terms of the nodal values of the given system, I can write a very simplified expression. I can say that u bar, which is a function of x of course, and I am now looking for not only the values in terms of u1 bar and u2 bar, but I have all the displacement parameters which are u1 bar, v1 bar, theta 1 bar, similarly u2 bar, v2 and theta 2 bar in the given system. So, if I now try to express this given function in terms of all these nodal values of the system, I realize I write here the first parameter n1, the v2 bar is not dependent, or v2 bar does not relate with the u bar in the given generalized function. So, I write it as 0. Similarly, theta 1 bar also does not influence the variation of the displacement along the longitudinal length of the member. So, this is also 0. u2 bar happens to be variation with the n2 function, and similarly the remaining two also come out to be 0. So, I realize now that this is a very standard expression which I can describe, which I can use to describe the variation of u bar in terms of a known function of x and the nodal values of the displacements of the given system. So, the nodal displacement values which we were initially looking for can now easily be expressed in terms of the standard shape function parameter and the vector containing the nodal values of the given system. So, if you go back to the expression which we initially started with, wherever the du bar upon dx appears in the given system, I can simply bring this idea over here and I can say that like the du bar upon dx can now simply be written as the derivative which will be commuted on the shape function vector, which is n1 0, n2 0, and the standard vector of the displacement field which we just described as say the capital U bar in the given system, that remains as same, that is not going to change in the given problem. So, the basic idea is that all the derivatives which are going to occur with respect to the function x in the given problem will all be taken up by the shape function parameters which are already known to the user, whereas the nodal displacement values will appear now in the expression for the given problem. And this so one can also note that this is the derivative if we are writing n1 with the dash sign here. So, this typically means d of n1 by dx. So, in this case we are using it, but do not try to confuse it with the notation which we used earlier for the local member coordinates and the global coordinates of the given system. These notations are specific to this particular part of the discussion. So, with this idea now we are in a position to identify the standard variations of the given primary displacement values across the length of the member, which are described in terms of only the nodal values of the given system and the shape functions which are the function of regular x parameter of the system. Similarly, one can also do it for the parameter of v1, v2 and theta 1 and theta 2 in the given system, but while doing it for the other two parameters of v1 theta 1 and v2 theta 2, one must also remember that theta 1 and theta 2 are not independent values. Theta 1 happens to be the derivative of the function v at the point 1. Similarly, theta 2 happens to be the derivative of function v with respect to x at the point 2 of the given system. So, now if I want to describe the variation of v1, v2, theta 1 and theta 2, I have to describe them in one similar function. Typically, in the standard finite element expression, we come up with something called as a Hermitian shape functions, which we use for this case. We are not doing this derivation again in this process, but one can easily refer any standard text on the finite element and we can get the Hermitian shape functions for this part. The one which I have derived here, these are the simplified Lagrangian shape function for the linear element. When we have only two nodal values identified, we can describe it by the linear function. Similarly, the process is very simplified. One can easily describe the variation of the v in terms of the standard function, which is now having 4 values, because you have v1 theta 1 v2 theta 2, 4 values in the system. So, I can describe it by the function a plus bx plus cx square plus dx cube in the given problem. Now, while describing the boundary conditions or the nodal values of the given system, I must define that v at or v bar at the position of x bar equal to 0 is equal to v1. This is the first condition. Similarly, v bar derivative with respect to x at the position of x bar equal to 0 is equal to theta 1. So, this way we can define two conditions. At the end 2 also I can define two conditions which will evaluate the values of the 4 unknown parameters in the given system, and that way we can define the generalized shape functions which will also describe the variation of the displacement parameters v1 theta 1 v2 theta 2 in the given system. So, this idea can be simplified in this manner, as we have shown that u bar can be expressed in terms of simplified shape functions of the given problem which we described, and similarly v bar can also be expressed in terms of the simplified shape functions which will be defined in terms of v1 bar theta 1 bar v2 bar and theta 2 bar in the given system. So, we have described them with the function of n1 and n2, which is 1 minus x upon L. So, I am now using x upon L in this function, but one can just understand that this is all in the local coordinates. So, if you are willing to keep it as a x bar, you can keep all the expressions with respect to x bar as well. So, with this idea we have defined all these functions in the given system, and just to make a continuity I will just keep everything with the x bar expression, so that it remains clear all throughout. So, with this point, now once we have identified these function fields, we now consider that the standard equation which we earlier described for the strain parameters can now be converted using these function of the shape or the shape functions of the given system. There is a reason to call them as a shape function also, because if you will just try to draw the distribution of them like between the two nodes of the given system, if we say the function is varying as 1 minus x bar upon L. So, the variation appears like this in the the variation appears like this in the given problem, Similarly, if I define the x upon L as a, so if I call it that this is n1. Similarly, if I draw the n2 which is x upon L, it comes out as this one in the given system. So, these are typically the functions which appear like that, how the specific degree of freedom is varying across the length of the given member, and that typically has its own set of properties which we generally discuss in a course on finite elements in the system. So, with this idea, now once I have this consolidated form, we write it as u bar is equal to this overall expression, and this we write as n of u in the given problem. Similarly, the second, which is v bar, we write this overall expression, that is n of v in the given problem, and that way we are able to now write that u bar is equal to n u of u bar and v bar is equal to n v of v bar in the given system. Now, using this idea, I can substitute the values in this part. So, as I substitute the values, I will realize that the first parameter du bar by dx can be written as d of nu by dx into u bar, plus the second parameter which is half of d v by upon dx whole square. So, it will come out as d of n v upon dx v bar whole square in the given system, and then the derivative of the v bar with respect to x, the second derivative. So, I can define it as d square n v upon dx square u bar in the given problem. So, this happens to be the standard way in which I can describe now the derivatives of the given system, but one must understand that n of u is itself a vector containing all the 6 values of the shape functions for the u bar field. Similarly, n of v is also a standard vector containing 6 values with respect to the v bar field, and these are described in this manner. Now, once I substitute these values, I write the expressions as I have written over here. As I said that d of nu by dx can be written as n of u prime. Similarly, this parameter can be written as n v prime, and this parameter, as it is the second derivative, can be written as n v double prime in the given system. Now, with respect to this parameters, I have expressed the basic relationship like this. To simplify them, now what we can also do, we can take a small variation in these strain parameters of the given system. The moment we take the variation, we must now understand that we are trying to change. So, variation means that we are trying to make a small change in the nodal values of the given system, which means that all those parameters which are function of the displacement field, they will be undergoing the variation, whereas the parameters which are not the function of the displacement terms, they will be remaining constant in the given system. So, with this idea, if I consider the first one epsilon x6, the variation in that, so the first parameter nu prime, I understand that this is all the function of x, it does not have any displacement parameter. So, it can be written as it is nu prime into del u bar. So, that has been taken outside the given system. So, or in a generalized manner, if I just write over here, it can be written as epsilon naught with a small variation in that, and I write this as nu prime, first one, because it will not undergo any variation because it is not a function in terms of any of the displacement parameters, into u bar, and that will be undergoing the variation. So, this is del u bar plus the half of, now this overall parameter is a one function which is defined with the square term. So, it is a function of the displacement as well. So, I will be taking first the derivative with respect to the function over here. So, it comes out as 2 times nu prime u bar, and then I will take the variation in the given system, and that variation will bring the nu dash in the same manner, sorry, nv as it is appearing there, into the variation on the u, which is del of u bar in the given system. So, you can just consider that I have taken, say, some function like x square, and if I now take the derivative on that, it will come out as 2 times of x into dx in the given function. So, this way I have expressed the overall system, which was made up of 2 parts, where nv prime was not the system to be undergoing the variation, whereas u bar was undergoing the variation in the given system. Now, with this idea in mind, we can now take u bar as a constant from both of these points, and that is what we are writing as a common term here, nu prime plus nv prime u bar, which is as a one single term we have adopted, into nv prime in the given system. So, we must understand that this is ideally one single term in the given problem, which can be related with the system as del v upon del x as a general part. Using the second parameter, we have this as a second term. If we write this parameter again in the variation, I get that as NV double prime, and this is simply undergoing with the variation in the given system, which means that if I write del of curvature term, it can simply be written as n of V double prime into del of u bar in the given system. So, this is how we express the standard form. Now, what we realize here, that del of E, which is written for the given system, is expressed in terms of some matrix term, because all of these terms, they are not the single valued, but they are themselves containing the 1 cross 6 vector form in the given system. Similarly, the n of V prime, this is also containing 1 cross 6 vector system in the given problem. So, this overall becomes a matrix. This is a del u bar. So, this is a relationship which is defining the condition of the beam's internal strain functions in terms of the nodal displacement values of the given system. So, you can correlate it that this is very similar to what we define in the truss problem as del of E equal to A into del u bar in the given problem. So, I can now consider that for a beam problem, this matrix which has been generated is same as the A matrix of the given system. So, now using this idea, we consider that the A as a parameter is the first term, which is nu prime nv double prime of the given system, plus nv prime u bar nv prime in the given system. Why did we separate these two terms? Because the first term, if you look at, is only a function of x in the given system, whereas the second term, if you look at, is also containing the u bar parameters, which means that this is a function of the displacement terms of the given system. So, any of the nonlinearity which will be introduced in the problem, where the stiffness contributions will become nonlinear, will be introduced due to this particular part of the given system. So, we write this as A equal to A naught, which is the linear part, plus A of n, which is the nonlinear part in the given system. Now, moving ahead with this, we write the general expression of the incremental stiffness part. We have already derived this in the previous session, if you can recall. I will just substitute now the values of the given system as we have written over here. So, del of epsilon, which is written over here, can be substituted with the value that A into del u bar. So, as I write the A into del u bar transpose, it becomes del u bar transpose A transpose k naught, and this is the epsilon, which is epsilon into dx for the given problem. This becomes as del u bar transpose p bar in the given system. So, this is not with the integral. Now, this expression can be further expressed as del u bar transpose, and at the same time k naught into epsilon, which is the standard part of the force parameter in the given system. So, I write it as the standard force parameter for the given system S, which is defined earlier, into dx integral of the given system, and this is equal to del u bar transpose p bar in the given problem. Now, what does this mean? That I can take del u bar, which is the first parameter in the system, over here also del u bar, which is there, which is not a function of x. So, I can take this out of the given, I think I missed one part. So, this is the del u bar transpose, and there is one A transpose as well. So, now I can take out this parameter of del u bar transpose out of the given x integral of the system, and by considering the similar terms on both the sides, we can write it as that p bar is equal to A transpose S into dx in the given system. So, this happens to be the standard expression which we utilize to correlate the nodal load values in terms of the internal stress values of the given system. We must recall that S in a general expression we have defined as a vector containing S of x and the moment component m of x in the given system. So, using this idea, I can now write that any of the small change in the load expression can be defined as dp bar is equal to the integral change again. So, A transpose, so a small change in A transpose into S dx plus integral of A transpose d of S dx. So, these are the two terms which we now get in the given system. We are again doing the similar process as we did in the truss members. We must recall that any of the derivatives or any of the small variation which we are taking, those are only taken on those terms which are function of the primary displacements of the nodal values. We realize that A is already a function of the displacement, as we have already seen in the previous part, and also the S, which is the axial contribution of the forces, were also defined that they are also the function in terms of the values of E of I, E of A, E of I into the strain parameter of the given system, and this strain parameter is again a function of the displacement field of the given system. So, using this idea, now we have again got two terms in the given process, first term which is identified like this, and the second term which is identified in this manner. I will take this term first to define the variation of the given system, similar to what we did earlier. So, with respect to this parameter, we get it as A transpose d of s dx integral in the given problem. Now, using this expression further, we realize that A transpose d of s in the given problem, as I write here, it contains the two parameter terms which are written in terms of the elastic properties of the given material, which are described by the K naught matrix, into the strain parameter of the given system. So, if I want to take the, and this is called as the overall S vector of the given system. So, if I want to take small variation in the d of s, it can be written as K naught, which is the same matrix, into d of epsilon in the given problem. So, with this idea, I write this expression as A transpose K naught into d of epsilon, and this overall as an integral expression of the given system. Now, what we realize that d epsilon in the given problem is equal to A into del u bar, as we have already seen earlier. So, I further express this expression as the first part of the expression, and I can write it as A transpose K naught del epsilon, which is A into del u bar. So, I am putting the dx integral together because du bar is not a function of x in the given system. So, I can take it outside the given system. So, as we are writing this part of the expression as a left hand side with equal to left hand side which is equal to d of p bar. So, we understand that this coefficient which is getting multiplied in this part is equivalent to the stiffness of the given system. So, we call it as the stiffness K A bar, as similarly we define in the truss problem also. And now we can just open up this expression for the given system. So, we will just try to see the expression in terms of the overall value, because A is defined with respect to A naught plus A n in the given problem. So, we will just try to add both the contributions to get the net value. As a second term, we got this parameter which is del of A transpose S into dx in the given problem. So, to substitute the value, what we will do in the given problem, we identify that the d of A in the given problem can be written as the standard value like this. Now, as a variation in the d of A, we realize that A is made up of two parts, which is A naught and A of n in the given problem. Now, if we look at the function of A of n, we have already seen that this is not a function of the displacement parameters. A remains, or the A naught term is a constant term with respect to the only function or the variation in terms of the x parameters, whereas A of n is the function which is defined in terms of the nodal values of the displacement. So, using this idea, I realize that when we start to take the variation in both of these parameters, d of the variation on the A naught will actually come out to be 0, because it is not changing with respect to the displacement function of the given problem. So, we have only the variation with respect to del of A n in the given problem, and when we substitute the del of A n, we realize that this is the expression which is there in the given problem. So, with respect to this parameter, we write the expression that d of A n which is shown over here. So, I will just write that the overall expression will become del of A n transpose S into dx, and this is the expression which we define. If we simplify this expression in terms of the values which we have obtained over here, we write it as n v dash transpose n v dash du bar transpose S x into dx. So, the idea over here is that d A n, which is having the two values of the given system, out of which one of the value is 0. If I consider this given function in terms of the transpose value, it will come out with the expression that n v dash du bar n v dash in the given system, and the second value will come out in the row now, because now I am taking the transpose of the given system. Now, this transpose will be multiplied with the S parameter of the system, and S value is identified as S x and the m x value of the given system. So, if I just multiply this with the S of x and m of x in the given system, I realize that the first parameter will give me the value which is identified over here, whereas the second parameter will not be giving any expression, because with the moment part I am multiplying the 0 value. So, with this idea in mind, we realize that the expression by multiplying these two parameters will only give you the expression in terms of the s of x in the given system, which means that the second term is going to contribute only with the geometrical stiffness in the given problem. So, with this we evaluated the geometrical stiffness term, which is evaluated over here, and this is the overall del u bar in the given problem. With this part, we understand that now this is the k of g in the given problem, which is also located in the member coordinate of the given system. Using this idea, now one can easily describe that k of t will be equal to k of a bar, which is identified in the first part, then the second, which is k of g of the given problem, and k of a is identified as a parameter which was written over here, del of a transpose k naught a into dx. So, this is the first parameter of the k of a, whereas k of g is defined over here, which is identified as nv transpose the s of x, which is the axial force in the system nv, and this is not the transpose with the given system, but it is the derivative with respect to the function of x as well, and this is integrated over the total domain. So, with these two values we can now evaluate the overall tangent stiffness matrix for the given system. So, this is the basic formulation which we follow for the standard beam problem. We have seen the steps are very similar to what we did for the standard standard truss problem as well. We will try to see some example cases in which we can implement it and check the suitability of the individual terms of the given system. With this we stop over here. Thank you everyone.